Good afternoon. This is Mechanics of Materials. Once again, we're working out of the 5th edition of the Hibbler textbook. So we're again working through chapter 11, entitled Bending. So our objectives here is to represent the internal shear and moment in a beam or shaft as a function of x, and we'll also be reviewing and going over the Flexure formula. So members that support loadings that are applied perpendicular to their longitudinal axes are called beams. And typically these beams are long straight bars having a constant cross-sectional area. And the three main beams we'll be talking about are classified depending on how they're supported. You have the simply supported beam, you have the cantilevered beam, and you have the overhanging beam. So because of the applied loadings, beams develop an internal shear force and bending moment that vary, that's the key word here, vary from point to point along the axis of the beam. So when we're doing our engineering design, since the shear force varies and the bending moment varies, when designing beams, it is important or imperative that you know the maximum shear and moment that the beam will experience due to its applied loadings. A way of doing this is to express the shear force V and bending moment M as a function of their position in the x direction along the beam's axes, and typically from left to right. So once you express both V and M as a function of their position x, you can then plot their values to get a graph where it will be easy to see the max values experienced. So like we said, the origin, when plotting as a function of x, is on the left, and positive values of x extend to the right. Now, beams support various loads, such as distributed loadings and concentrated forces. Because of the different loads beams can support, the plots or equations as a function of distance x must be determined for each region of the beam between any two discontinuities of loading. Let's talk about beam sign convention. So if you're distributing loading x upward on the beam, then it's positive. if your internal shear force causes clockwise rotation, then it's positive. And the internal moment causes compression or a tendency to bend the beam where it would hold water, then that's positive as well. If it causes a tendency for the beam to bend where theoretically it will be able to hold water, then that's a positive direction for your internal moment. Loadings opposite to these directions are obviously negative sense. So take a look at an example problem of what we mean here. Let's take a look at a textbook example. This is 11.1. This is page 502 in text. They want you to draw the shear and moment diagrams for the beam. So right off, we know this is a simply supported beam. Pinned on the left-hand side and a roller on the right-hand side. And is subject to a distributed loading of 3 kilonewtons per meter. As a rectangular loading, the length is 4 meters. So first, let's do our free body diagram to get our support reactions. So we said this is a roller, and this was a pin. And one thing to note, we're primarily concerned with shear, vertical direction forces, and any moments that may arise due to the supports. So a free body diagram, we can represent the distributed loading by its resultant force, 3 kilonewtons per meters, base times height, the area under the loading diagram. So this would be 3 kilonewtons per meter times 4 meters. This comes out to 12 kilonewtons and is applied per our appendix B directly in the center. We'll call this BY for the roller, and we have an AY and an AX for the pin. So if we take the moment about point A, set it equal to 0 for our equilibrium conditions, we have BY and counterclockwise is positive, clockwise is negative. You have BY times 4 meters minus your 12 kilonewton resultant force times 2 meters equals 0. BY is 6 kilonewtons. Then we do our sum of our forces in the y direction equals 0. You have your AY minus your 12 kilonewtons plus your 6 kilonewtons equals 0. AY is 6 kilonewtons. So now we can redraw the initial beam with its vertical forces. You have 6 kilonewtons on the ends, and you have 12 kilonewtons downward force in the middle. So what we're looking to do is plot our shear force as a function of its position x. So here we're just dealing with one force, the one applied force. We just have one applied loading. So if we represent the beam and we section, no, let's change that a little bit different. We're dealing with one applied loading, and our position x goes from the left at x equals 0 to a maximum of x equals 4 meters. And we want to know the internal shear force as a function of this x from x equals 0 to x equals 4 meters. So now we'll put everything as a function of x. So this distance now becomes x. We have our internal shear we're trying to define, and our bending moment m. And we default to our positive values here. Remember, if the internal shear tends to cause a clockwise rotation, is positive. The bending moment tends to compress the fibers upward, is positive. So those are our two unknowns we want to get. So if we plot from the left segment of the beam, then we have to account for our support reaction here, 6 kilonewtons. And this is for 0 less than equal to x less than equals to 4 meters. This is our range. So here comes the interesting part. The distributed loading is rectangular, which means it's the area under the loading curve, base times height. And when we did our initial free body diagram for the beam as a whole, we did the base 4 meters times the height of the loading, 3 kilonewtons per meter. But now we want to do it as a function of x. So this base now will be written as a function of x. Therefore, the resultant force base times height will be base we'll say height 3 kilonewtons per meter times the base x. Six kilonewton support reaction. This is the left segment. And we're plotting or solving for V as a function of x. So this distance now is x, and x we said is from 0 to 4. X is a minimum of 0 meters and a maximum of 4 meters. So if I do the sum of my forces in the y direction, so I can solve for the V, we have to take into account the 6 kilonewton support reaction on the left-hand side. minus V, because V is in the negative direction, minus the loading. So the loading would be the height, the 3 kilonewtons per meter times the X, the base. So rearranging this equation, plus V on both sides, you have V is 6 minus 3x. And this is in kilonewtons. So what this means then for X and V, if you want to put a chart, when X is 0, V is 6 minus 3 times 0, 6. And this is kilonewtons. X is in meters. When X is equal to 1, V is equal to 6 minus 3 times 1. When X equals 2, V is equal to 6 minus 3 times 2. When X equals 3, V is equal to 6 minus 3 times 3. Likewise, when X equals 4, V is equal to 6 minus 3 times 4. So as you can see here, if we were to plot this, x-axis, let's go to a clean page. And we went from 630 minus 3 minus 6. So if you were to plot this curve, the x-axis, and then our V in kilonewtons, this is in meters, and this is our origin. So it starts at a high of 6, and is a linear curve. So this is the this is the shear diagram for that simply supported beam as a function of X. Therefore, the maximum shear experienced by the beam is 6 kilonewtons. And it's at the two ends is where this is experienced. So continuing along, because they want us to construct the moment diagram as well, we'll reproduce our left segment of the beam, taking into account our 6 kilonewton support reaction. And our resultant force here, which is as a function of X, base times height. So that'll be 3 kilonewtons per meter times X. So for our moment, so that we take into account our bending moment M, and we'll always take in a moment at the point to the right. Say location. So we'll take the moment as a generally statement at the location of our unknown bending moment M. So at that point here, our moment would be counterclockwise rotation is positive. So M minus 6 kilonewtons times the distance here. Well, we're getting it as a function of x, so the distance from here will be times x. Now we need to know the distance from where the resultant force of the distributed loading acts to the right. Well, this is a rectangular loading. So for a rectangular loading, the resultant force is always in the middle. And for whatever this length is, the base, each side will always be the base length over 2. This is for a rectangular loading. The length is always b, and the distance on each side of where the resultant force is applied is that length b over 2. It's directly a half. Half on each side. So applying that here for it, where the resultant force acts to the right will be is counterclockwise, so positive rotation. So that'll be 3 times x. This is the force. So for moment, we need a perpendicular distance, which would be x over 2. Rearranging that equation, you have m minus 6x plus 3x squared over 2. Getting m on the side of the equation by itself, you have m equals to 6x minus 3x squared over 2. So once again, m is equal to 6x minus 3x squared over 2. So x in meters, m is in kilonewton meters. Zero, 1, 2, 3, 4. When x equals 0, m is 6 times 0 minus 0. So this m is 0. When x equals 1, m is equal to 3 times 1 squared, 3 over 2, which is 1.5. 6 minus 1.5, which is 4.5. When x equals 2, m equals to 2 squared is 4. 4 over 2 is 2. 6. When x equals 3, that's 9 times 3. 27 over 2. When x equals 4, 20, so 0. So then the curve here for the moment diagram, the m is in kilonewton meters, your x is in meters. The ends, this is your origin, and you have a high of 6. So your maximum bending moment is at x equals 2, m is 6 kilonewton meters. Let's take a look at another problem. Let's take a look at your textbook example 11.3. This is page 504 in text. Once again, it wants us to draw the shear and moment diagrams for this beam. It's another simply supported beam. It's a pin here and a roller here. So it has a trapezoidal loading. Which we can make into a rectangular and a triangular loading. The rectangular loading intensity is 2 kip per foot. And the triangular loading intensity would be, this is 2 kip per foot. So this would be 4 kip per foot, kilopounds per foot. The total length here is 18 feet. So first, let's do our free body diagram to get our support reactions. And we'll say the pin at A, we'll say a roller at B. So we'll take the sum of our moments about A equals 0. Well, first, let's see what it looks like. The rectangular loading is base times height and be right in the center. So it'd be 9 feet from either end. And that would be 2 kip per foot times 18 feet, which would be 36 kilopounds. The triangular loading would be 1/2 base times height, which would be 1/2 the base, which is 1/2 of 18 feet is 9 feet, times your 4 kip per foot comes to 36 kip. And this is applied a third from the right hand side. So this will be 6 feet from the right hand side. So then back to solving for our support reactions. If we take the pin at A, the moment about point A, then this leaves the roller at B, and counterclockwise is positive. So we have the triangular loading force, 36 kip, times the perpendicular distance to point A, which would be 6 feet, plus the rectangular loading times its perpendicular distance, 9 feet, minus by the roller times the total length, 18 feet, equals 0. Solving for by, we get 30 kilopounds. Then, using our sum of our forces in the y direction, you have your by, which is 30 kilopounds, minus your 36 kip from the rectangular loading, minus your 36 kip from the triangular loading plus your AY from the pin at A. Your vertical loading, your vertical support here is equal to 42 kilopounds. So once again, where are we going? We're trying to get the shear and the bending moment as a function of the distance from left to right, x. So similarly to the previous example problem, for rectangular loadings, which are represented by base times height, as a function of x, there's simply your intensity, which would be 2 kip per foot times whatever distance x you're working on. So this would be represented in this problem 2x. However, for your triangular loadings, we have to do a proportion. So we know for a triangular loading, it's equal to the area of the curve, half the base times the height. So initially we were giving, for the total length of 18 feet, the loading was 4 kip per foot. So we have 4 kip per foot for 18 feet is our new intensity W over x feet. Rearrange, you have W is 4 over 18 times x, and this would be kip per foot. So with that being said, let's look at our free body diagram of the left segment. Taking into account our roller support reaction, 30 kilopounds, which we've already solved. We have our rectangular loading. So if this distance is x, our rectangular loading is applied x over 2 away from both sides. And is represented then by base times height, 2x. For our triangular loading, this is applied a third from the large side, from the end. And this resultant force would be our W we solved for, which is 4/18 x times, so half the base times the height times 1/2 the base x. So once again, the area under the triangular curve would be 1/2 the base, which is 1/2 x, times the intensity, which is 4/18 times x. And we have to take into account what we're unknowns we're solving for, our v, our shear force v, and our bending moment m. So for the sum of our forces in the y direction equals 0. Taking into account our support reaction at the roller, 30 kilopounds, minus our rectangular loading, which is 2x, minus our triangular loading, which is 4/18 x times half x, minus our v. Let's go to a clean page and rewrite that. You have your 30 kilopounds minus your 2x from your rectangular loading, minus your 1/2 x, 1/2 the base, times the height, which is 4/18 x, minus v equals 0. Rearrange this equation for v, which means plus v on both sides. You have v equals to 30 minus 2x minus x squared over 9. And this is in units of kilopounds. So for our moment now, let's draw it once more. We're taking the moment, remember, always at the point where our internal bending moment is. So it will be everything, the perpendicular distance from here. So for instance, the 30 kip, the perpendicular distance to the bending moment m would be the total length x, 30x, force times distance. So for our moments, we take into account our m, the bending moment, counterclockwise inducing rotation is positive, clockwise inducing rotation is negative. So it'll be m minus your 30 kip times your total length x. Taking into account the rectangular force, that would be 2x times the perpendicular distance, which we said is x, always x over 2. Rectangular loadings, the concentrated force is applied directly in the middle. For the triangular loading, the force is 1/2 the base, which is 1/2 x, times the height, which is 4/18 x. So that's our force component here, times the distance, which would be x over 3, 1/3 x, always to the larger side, equals 0. So rearranging this equation, this would be 30x minus 2x times x over 2 is x squared, minus x times x times x is an x cubed, 1/2 times 4/18 divided by 3 This is x cubed over 27. And these units are kip feet. So likewise, we've now have our V and our M as functions of x. And you can plug it into your calculator to plot, or you can do it by hand as we did with the previous examples. Either way, how the curves come out for your V, which is in kilopounds, x in feet, $30 kilopounds that's how the curve looks for the internal shear force. For the bending moment, M is in kip feet, x is in feet. The max here is 163 kip feet. And your maximum moment occurs when V equals 0. Take a look at some problems. Look at problem 11-1. This is page 518. So I wanted to draw the shear and moment diagrams for the shaft and determine the shear and moment throughout the shaft as a function of x. So first, let's find out support reactions. A and B exert only vertical reactions on the shaft. You have your AY, you have your 800-pound force here, you have your BY, and you have a 500-pound force here. This distance here is 3 feet. This distance here is 2 feet. this distance here is 1.5 feet. So we take out some of our moments about point A. Counterclockwise is producing rotation is positive. So you'll have your By times your 5 feet minus your 800-pound force times your 3 feet minus your 500-pound force times 6.5 feet equals 0. By comes out to be 1,130-pound force. Take your sum of forces in the y direction. You have your AY minus your 800-pound force plus your 1,130-pound force and minus your 500-pound force. AY is 170-pound force. All right, so then for the range of X, from 0 to 3 feet, the left segment looks like such. We have to take into account our support reaction of 170-pound force. This distance would be X. Taking into account our V and our moment, M. So sum of our forces in the y direction, you have your 170 minus your V equals 0. So V is 170-pound force. Your moments at this point here, taking into account your M minus your 170-pound force times the perpendicular distance X equals 0. So your bending moment is 170 X. And this is pound force feet. So for your next range of X, that's between 3 feet to 5 feet. Taking into account our support reaction, 170-pound force. We have an 800-pound force here. This distance is 3 feet. Taking into account our V and our bending moment, M. Some of our forces in the y direction. You have your 170-pound force minus your 800-pound force minus your V equals 0. Your V is equal to minus 630-pound force. Taking your moment, some of your moments here. You have your M. minus your 170-pound force times your total distance, which would be x, plus your 800-pound force times the distance here to here. So if the total distance is x, and we know this distance here is set at 3 feet, then the difference from here to your point you're taking your moments at is your total distance minus the 3 feet. So times x minus 3 feet equals 0. So your bending moment M is minus 630x plus 2400, and this is in pound force feet. Continuing along, the last range the problem is asking for between 5 feet and 6 feet. So taking into account our 170-pound force, our 800-pound force, this distance is 3 feet. Our BY, which was 1130-pound force, this distance here is 2 feet. So taking into account our V and our bending moment M, sum your forces in the Y direction. You have 170-pound force minus your 800-pound force plus your 1130-pound force minus V equals 0. Rearranging that, plus V on both sides. V is 500-pound force. We're taking our moments here. So you have your bending moment M. Counterclockwise positive. So you have your M minus your 170x plus your 800 times x minus 3 minus your 1130-pound force times x minus 5 equals 0. Rearranging that equation, you have 170x, and moving it to the other side of the equal sign, you have minus 800x plus 2400 plus 1130x minus 5,650 equals 0. I mean, sorry, not equals 0. you get M equals to, combining like terms, M is equal to 500x minus 3250. And this is units of pound force feet. So then it's asking us to plot this. So let's do a quick recap. For your 0 less than equals to x less than 3 feet, your V is 170 pound force, and your M was 170x pound force feet. For your 3 feet less than x less than 5 feet span, your V is minus 630 pound force, and your M was minus 630x plus 2400 pound force feet. And for your 5 feet less than x less than equal to 6 feet, your V was 500 pound force, and your M was 500x minus 3250 pound force feet. So plotting these, x in feet, V is in pound force. This is 170. And this is from 0 to 3. X equals 3. Then it goes down to minus 630. It's from 3 to 5. And then up to, this is 500. For your moment diagram, the y-axis is your moment, pound force feet. When x equals 0, M is 0. This range is 510 pound force feet. This is minus 750 pound force feet. It's minus 250. Let's take a look at another problem. Problem 11-5. This is page 518 in your text. They want you to express the internal shear and moment in the cantilevered beam as a function of x, and then draw the shear and moment diagrams. So we have a triangular distributed loading. So let's start with our free body diagram. Of the beam. This is 6 feet in length. You have a 300-pound force at the end. This is 200-pound force per foot. The intensity here. Cantilevered at A. And we know from our table 4.1, in chapter 4, for support reactions, cantilevered or fixed in, you have to account for a moment as well as your X and Y direction forces. Okay. So our resultant force from the triangular loading is half the base times the height. So it'll be somewhere right here. We 1/2 6 feet times 200-pound force per foot. So 600-pound force. And that's 2 feet from the end. Where is it applied? So for the fixed end at A, you have to account for your AY as well as your moment reaction for the support. So some of the forces in the Y direction for the support reactions, you have your AY minus your 300-pound force minus your resultant of the triangular loading, which is 600-pound force, equals 0. Your AY is 900-pound force. And your moment here, let's say moment at A. Your moment at A we'll say it's equal to your 300-pound force times the perpendicular distance, which is 6 feet, plus the 600-pound force times your 2 feet equals 0. This is equal to 3,000-pound force feet. So that's our support reactions. So now to start working with the internal shear and internal moment. Looking at the left segment of the beam, taking into account the 300-pound force, got your shear and your bending moment. Now for the triangular loading, once again, we have to figure out its proportional distributed loading. Well, for a triangular loading, like we said previously, that's 1/2 the base times the height. Here, the base would be x. So we know for the original length, there is 200-pound force per feet to 6 feet as your W, the loading we're looking for now, for x feet. Rearranging this equation, you have W is 200 over 6 times x. So this is 33.3x. It's our new loading intensity. So where it is applied, if this distance now as a function of x is x, so this is applied, the resultant force of that loading would be half the base, so half of x, times the height, which is 33.3x. So now, some of our forces in the y direction, we have minus 300-pound force minus your 1/2 x times your 33.3x minus v equals 0. Rearrange this equation, put the v to the other side. V is equal to minus 300 minus 16.67 x squared. This is units of pound force. Taking my moment, you have your bending moment M plus your 300-pound force times the total distance x plus your triangular loading force, which is 1/2 x times 33.3x times the perpendicular distance, which in this case is always x over 3, is a third from the end. Rearranging this equation, you have your moment, bending moment is negative 300x minus (5.56) x cubed, and this is in units of pound force feet. So to recap that, our shear, internal shear force as a function of x is minus 300 minus 16.67 x squared pound force. Our bending moment, minus 300x minus 5.56 x cubed. This is pound force feet. Plotting these diagrams, like I said, you can use your graphing calculator or Excel. V is in pound force. X is in feet. Minus 300 when x is 0. minus 900 when x is equal to 6. Your bending moment diagram. This is pound force feet. Is 0 when x is 0. And minus 3,000 pound force feet when x is equal to 6. So now we'll begin talking about the Flexure formula. This is an equation that relates the stress distribution within a straight beam to the bending moment acting on its cross section. So we make some assumptions. The material behaves in a linearly elastic way. So Hooke's law applies. So your bending stress will vary from 0 at the members or beams neutral axes to a maximum value at a distance C, which is the farthest distance away from the neutral axes. So what is the neutral axis? Sometimes abbreviated NA. The neutral axis is the horizontal centroidal axis for the cross section. So, in other words, determine the members centroidal or centroid of the cross-sectional area then you know the neutral axis location. And this is back to our chapter 6 and appendix B concepts. So our flexure formulas are equals the maximum normal stress in the member M is the resultant internal moment and is calculated about the neutral axis. C is the perpendicular distance. From the neutral axis to a point farthest away from the neutral axis. And I is the moment of inertia of the cross-sectional area about the neutral axis. Let's take a look at a problem. Problem 11-48. This is on page 538. They want you to determine the moment that produces a maximum stress of 10 KSI on the cross section. So first you need to locate your Y bar, which is the centroid of this composite shape. And this is chapter 6 concepts, where our Y bar is equal to your sum with the wide wiggly bar is the coordinates of the center of gravity of each of the composite parts of the body. So we know the way we work this out is setting up our table and our area. I guess we have inches squared here. So for this composite shape, we're basically having 4 rectangles, 2 of which are equivalent. So we'll label this 1, 2, 3, 4. Those are 4 segments, 1 and 4 being equivalent. So the area of segment 1, which is the same as segment 4, is 3 inches times the width, which is 0.5 inches. 3 inches times 0.5 inches. The area for segment 2, base times height, is 3 plus 0.5 plus 0.5. So that's 4 inches times the height, which is 0.5 inches. The area for segment 3 is 10 inches times 0.5 inches. The location of the centroid and our distance y bar is coming down this way. So for segment 1, the location of, and segment 4, they're the same. The location of our y wavy bar for the location of the centroid of those individual shapes. For segment 1 and segment 4, they are a distance of 0.5 inches plus 1.5 inches. So that's 2 inches. For segment 2 is at a distance of 0.5 divided by 2, which is 0.25 inches. And for segment 3, you have to take into account the 0.5 inches of segment 2 down to the half of 10. So that's 5 inches plus the 0.5 inches. That's the distance. So the rest then is multiplying it out. So your sum of your areas And your sum of your y wavy bar A (10 inches squared). Your y wavy bar A sum is 3 plus 3 plus 0.5 plus 27.5, 34 inches cubed. So let's recap it. Your sum of your area is 10 inches squared. 34 inches cubed. So your y bar for the whole composite (34 inches cubed over 10 inches squared). This is 3.4 inches. So this is located 3.4 inches from the top. So that's our centroid axis of the composite shape. So now we have to determine our I. And we know from Appendix B and this is on page 815, for a rectangular area, I sub x is equal to 1/12 the base times the height cube. Do not forget about the cube. So reverting back to our chapter 6 concepts, our parallel axes theorem. So the moment of inertia then for the shape is for segment 1 So for segment 1, 1/12 the base times the height cube. And remember, segment 1 and segment 2 are, segment 1 and segment 4 are identical, so we'll put 2 times. So it's 1/12 the base. The base is 0.5 inches times the height cube, the height being 3 inches, plus the area, which is base times height 0.5 inches times the height, which is 3 inches, times dy squared. Dy is the distance from the composite shape centroidal axes, the 3.4 inches, to the individual centroid of each shape that makes up the composite. So in this case, it would be the 3.4 inches minus the 2 inches, which is the centroid location of segments 1 and 4. So that's for segments 1 and 4. Segment 2, all is a rectangular shape, so 1/12 the base being 4 inches, times the height, which is 0.5 inches cubed, plus the area, which is base times height, times dy squared. Don't forget the squared. The difference here is 3.4 inches minus the location of the centroid for segment 2, which is 0.25 inches squared, plus for segment 3, once again, it's a rectangular shape, so it's 1/12 the base, which is 0.5 inches, times the height, which is 10 inches cubed, plus the area, which is 10 inches, times 0.5 inches, times dy squared, which is the difference in the centroid location of segment 4 to the overall composite, which is 5.5 inches minus 3.4 inches squared. Solve this out. Your moment of inertia gives you 91.73 inches to the 4. So our flexure formula we were given the maximum stress Now the distance C is the farthest distance away from the centroidal axes. So the centroidal axis, Y bar, is 3.4 inches. From the top, the farthest inches away will be the total length minus that. So 10 inches minus the 3.4 inches. That's our C. Farthest distance away from Y bar. And our moment of inertia, I, we determined previously as 91.73 inches to the 4. So rearranging this equation, solving for M, this comes out to 129.2 kilopounds inches, which is what the problem asked for. So we'll stop here today. Please feel free to send me an email if you have any questions. And until next time, be safe.